Today I will discuss about the important questions and answers of atomic structure. Our first topic is Bohr's atomic model. Now the first question of this topic is find out the radius of the first shell of Li2 plus ion. Li2 plus ion is a hydrogen-like system. That means it contains one electron system. Now we have a formula to solve this type of problem. The formula is Rn equals to 0.529 into n square by z angstrom, where n equals to number of shell which has to be calculated, z equals to number of proton of the species, and Rn equals to the radius of the shell. Now according to our question, the answer will be radius of Li2 plus ion will be 0.529 into n square. N means first shell, that means 1 square. Z, number of proton present in Li is 3 angstrom, so the answer will be near about 0.176 angstrom. So this is our answer. Now our second question is what is the energy of the second shell of hydrogen atom? Now we have a formula to solve this type of problem. That is En equals to minus 13.58 into z square by n square eV. That means electron volt. Now we have to find out the energy of hydrogen atom for second shell. So for hydrogen atom, the value of Z, that means number of proton, is 1. So 1 square. Now we have to calculate the energy for the second shell. That means here the value of N will be 2. So 2 square. Now after calculation, we have the answer minus 3.395 eV. So it will be our answer. Now our third question is calculate the ionization energy of hydrogen atom and He+. The ionization energy, basically the energy required to remove one electron from its valence shell. Now in case of hydrogen atom, the electrons is present in the first shell. Now what is the energy of this first shell? E1 equals to minus 13.58 into 1 square by 1 square. This one is basically the atomic number of hydrogen atom, and this one is the value of the principal quantum number of the first shell, that means 1, and the unit is electron volt. Now we have to remove this electron from the first shell to this infinite shell. Now what is the energy of this infinite shell? E infinite equals to minus 13.58 into 1 square, that means atomic number, 1 square and the principal quantum number of the shell, that means infinite. So this will be 0, E infinite will be 0. Now the ionization potential or ionization energy equals to E infinite minus E1. That means 0 minus of minus 13.58 eV. That means 13.58 eV. So ionization potential of hydrogen atom is 13.58 eV, and this is our answer. Now for helium ion He+, the energy of the first shell will be minus 13.58 into 2 square by 1 square, 2 atomic number and 1 principal quantum number of the valence shell. Unit is eV. And E infinite, the energy of the infinite shell will be minus 13.58 into 2 square by infinite square eV, that is equals to 0 eV. Now the ionization potential of helium ion will be E infinite minus E1, that means 0 minus of 13.58 into 4 eV. After calculation we get 54.32 eV. This is our answer. So the ionization potential of helium ion will be 54.32 eV. Our second topic is atomic spectra. Now our fourth question is calculate the wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. Now we have a formula to solve this problem. Nu dash equals to RH, that is Rydberg constant, into 1 by Nf square minus 1 by Ni square. Now what is Nf and Ni? Suppose one electron is present in this shell called Ni, and when it is jumped from Ni to Nf, then a certain amount of energy is released, which is called spectra. Now in case of Balmer series, Nf always 2. Here we have to find out the longest wavelength. That means longest wavelength, that is delta E, will be maximum because delta E is inversely proportional to lambda. Now when the lambda is maximum, delta E will be smaller or minimum. Now in case of longest wavelength of Balmer series, Ni will be 3. That means the adjacent shell of the second shell. Now electron jumps from third shell to the second shell. So our answer will be RH, that is Rydberg constant, is equals to 1.097 into 10 to the power 7. Nf equals to 2, so 1 by 2 square minus 1 by 3 square. because the initial shell is 3 and the unit is meter inverse. So after calculation we get 0.15 into 10 to the power 7 meter inverse. That means 1.5 into 10 to the power 6 meter inverse, and this is our answer. So the wave number for the longest wavelength in Balmer series for atomic hydrogen will be 1.5 into 10 to the power 6 meter inverse. Our fifth question is, calculate the number of spectral lines observed when an electron jumps from fourth shell to the first shell. Now we have a formula. Number of spectral line equals to n2 minus n1 into n2 minus n1 plus 1 by 2. What is n2? n2 equals to the initial shell, and what is n1? It is final shell. Now electron jumps from fourth shell to the first shell. So the number of spectral line will be four minus 1 plus 1 by 2. That means 3 into 4 by 2. So 6 will be our answer. So total number of spectral line observed when an electron jumps from fourth shell to the second shell, the total number of spectral line will be 6. That means when electron jumps from fourth shell, that is n equals to 4, n equals to 3, n equals to 2, n equals to 1. Electron jumps from fourth shell to first shell. Now one spectral line will be observed. Electron can jump from fourth shell to the third shell, then fourth to second shell, then second to first shell. Again electron jumps from fourth shell to the third shell, then third shell to the second shell, and then second shell to first shell. Again electron jumps from third shell to the first shell. So the total number of spectral line will be 1, 2, 3, 4, 5 and 6. Now using this formula we can easily calculate how many spectral line will be observed when an electron jumps from n2, that is initial shell, to n1, that is final shell. Our next topic is de-Broglie equation. Now the sixth question is, calculate the momentum of a particle which has a de-Broglie wavelength of 0.1 nanometer. Now the de-Broglie's wave equation is lambda equals to h by mv, where lambda is the de-Broglie's wavelength. This is wavelength. H equals to Planck constant. Planck constant. mv is equal to the momentum of the electron. Now we have to find out the momentum, so mv equals to h by lambda. Now h equals to 6.626 into 10 to the power minus 34 and lambda is 0.1 nanometer, that means 0.1 into 10 to the power minus 9 meter. So the unit of momentum will be kg meter per second. Now after calculation we get 6.626 into 10 to the power minus 24 kg meter per second, and this is our answer. Our next topic is Heisenberg's uncertainty principle. The question number 7 is calculate the uncertainty in position of an electron which has uncertainty in momentum is 6 into 10 to the power minus 2 kg meter per second. Now according to Heisenberg uncertainty principle, the product of measurement in the uncertainty in momentum and the uncertainty in position will be equal to h by 4 pi. Now delta x will be h by 4 pi into delta p. H, that means Planck constant, is equals to 6.626 into 10 to the power minus 34 joule second, and 4 into pi, that means 3.14 into delta p, that means given in the question delta p value is 6 into 10 to the power minus 2 kg meter per second. After calculation we get 8.8 into 10 to the power minus 34 meter, and this is the uncertainty in the measurement of position of this electron, and this is our answer. Our next topic is quantum numbers. The 8th question of atomic structure is find out the set of quantum number of the valence electron of sodium atom and the unpaired electron present in chlorine atom. Now for sodium atom, the electronic configuration is 1s2, 2s2, 2p6, 3s1. Now we have to find out the set of quantum number of this electron. Here the principal quantum number n equals to 3. In case of s orbital, the value of L will be 0. For S, L equals to 0. For P, L equals to 1. For D, L equals to 2. And for F, L equals to 3. Now this electron present in s orbital, so the value of L will be 0. Now the value of m, that is magnetic quantum number, L is azimuthal quantum number. Now the magnetic quantum number will be calculated as minus L to plus L. Now the value of L is 0. So minus 0 to plus 0, that means the value of M is 0. Now the last quantum number, that is spin quantum number, S, equals to plus half, because one electron present in s orbital, and here we will consider this electron, the spin of this electron is clockwise, so this is represented as plus half. So the set of quantum number will be 3, 0, 0, plus half. So this is the set of quantum number of sodium atom. Now for chlorine atom, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So if we draw the box diagram of 3p orbital, this is 2, 3, 4, 5. Now we have to find out the set of quantum number of this unpaired electron. Now this electron is present in the third shell, that means n equals to 3, that is principal quantum number. Now the azimuthal quantum number L equals to 1, because for p orbital L equals to 1. Now n equals to 3, L equals to 1, and the magnetic quantum number is considered as -1, 0 and +1. Now the electron is present in the pz orbital, so the value of m will be 1, and the spin quantum number is, it will be plus half. This electron is supposed to be, has a spin plus half. So the set of quantum number of this electron, that means the unpaired electron present in the chlorine atom, will be 3, 1, 1 and plus half. So this is our answer. Our next topic is Ohm's rule. Ninth question of atomic structure will be, write down the electronic configuration of chromium and copper atom. These two elements has exceptional electronic configuration. It is expected that chromium atom has the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, because the atomic number of chromium is 24. But if we draw the box diagram of the valence shell, 4s and 3d, then it is observed that the 3d orbitals are not half filled. So due to gain stability, one electron will be promoted from 4s to 3d orbital, and after that this type of configuration will be observed. So this is 3d and this is 4s. Why this electron get promoted from 4s to 3d? Because 3d orbitals are now half filled. So according to Ohm's rule, half filled orbitals are more stable. So electron jumps from 4s to 3d orbitals and form a half filled orbitals, half filled 3d orbitals, and this is stable. So that is why chromium has electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. This is chromium's original electronic configuration. Now in case of copper atom, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. This is our expectational electronic configuration, but the original configuration will be differ from this. So when we draw the box diagram of copper atom, of the valence shell of copper atom, then we observe that this type of configuration. This is 4s and this is 3d. Sorry. This is the expectational electronic configuration of copper atom. Now one electron can jump from 4s to 3d. So the configuration will be this is the electronic configuration of copper atom. This electron jumps from 4s to 3d orbital to gain stability. Now copper atom is stable, so the electronic configuration of copper atom will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d10. So this is the electronic configuration of copper. Question number 10 of atomic structure. Calculate the number of unpaired electron present in Cr3 plus and. So the electronic configuration of chromium atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Now the box diagram of the valence shell is like this: 4s1 and 3d5. Now when 3 electron removed from chromium atom, we get Cr3 plus, and the electron will first remove from 4s orbital, then 3d orbital. So the electronic configuration of chromium atom will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s0 and 3d3. So the valence shell electrons present in 3d orbitals are 3d3. So the number of unpaired electron present in chromium atom is 3. So our answer is 3. Number of unpaired electron present in Cr3 plus is 3, which is present in 3d orbit. If this video is helpful to you, then like, comment, share and subscribe us. Thank you.